Welcome to the deep dive. Today, we're really getting into the shift that's happening in data centers, moving away from doing everything by hand towards this idea of intent-based automation.
Exactly.
Our mission here is to sort of break down the key pieces of modern data center networking, the physical design, this EVPN-VXLAN overlay stuff, and then how Juniper Apstra fits in to automate it all.
Yeah.
We want to give you those core insights, the stuff that really aligns with the specialist level knowledge for that JN0-481 cert.
That's a great way to put it. The source material really connects these dots. You can't truly grasp Apstra without understanding why EVPN can get complex.
Right.
And you can't really run EVPN well without the right physical setup underneath. It all builds. The whole exam, 90 minutes, 65 questions. It's about seeing those connections.
Okay, so let's unpack this then. Got to start at the bottom, right? The physical network, the actual wires and switches. What's the standard recommendation these days for a scalable, high-performance IP fabric? Not the old three-tier thing.
Yeah, forget core E-access mostly. The standard, now, the one Juniper and pretty much everyone pushes, is the three-stage closed topology.
Okay.
But everyone just calls it spine leaf.
Spine leaf. We hear it all the time, but I think it's really important for you listening to get why it's better. What makes spine leaf the winner, especially with all that east-west traffic inside the data center now?
Well, the big thing is predictability, and that leads directly to better performance.
Predictability. How so?
Because in the old models, traffic might have to go way up to a core switch, then back down, maybe hitting different policies.
Yeah.
It was variable.
Right.
With spine leaf, every leaf switch is exactly one hop away from every other leaf switch through a spine, always the same path length, topologically speaking.
Ah, okay. Consistent latency then.
Exactly. Predictable latency.
Yeah.
And the other key part is how you use all those paths.
You mean getting the traffic spread out?
Yeah, that's where ECMP comes in. Equal cost multipath routing.
ECMP. Oh.
That's the magic behind achieving or getting close to non-blocking bandwidth. Every leaf has multiple equal cost paths up to the spines.
So the network just uses all of them at once?
Pretty much, yeah.
Yeah.
IP routing naturally load balances across them. It gives you amazing resilience, too. It makes scaling out horizontally much easier. Need more capacity, just add another spine or more leaves.
Simple in concept, powerful in practice. Okay, so we've got our scalable physical underlay, spine leaf using ECMP, solid foundation.
Right.
Now let's move up a layer. From the physical pipes to the virtual overlay, where we handle things like multi-tenancy, that's where EVPN-VXLAN comes in. This used to be super complex. What protocol handles the control plane now in these modern fabrics? How do switches learn where everything is?
Well, this is where it gets pretty interesting. The control plane actually relies on BGP.
BGP, like Border Gateway Protocol, the Internet Routing Protocol.
The very same. It's a huge shift. Traditionally, layer 2 info is all flood and learn, lots of broadcast storms. Painful stuff.
Oh, yeah. Been there.
In an EVPN-VXLAN world, BGP is used inside the fabric to pass around host reachability info, MSA addresses, IP addresses, VTP information between the leaf switches. Much more efficient.
So BGP is doing double duty now, inside and potentially outside. It's managing where hosts are, even if they move. That's like the core of EVPN, right?
That's the essence of it, yeah. Using BGP's strengths for scalability and reachability within the data center.
Okay, so if BGP is the vehicle, it needs specific ways to carry this EVPN data, different route types, I guess. Which specific route type is the real workhorse here, the one carrying, say, the VTPN address and the NC address for a host connected to a leaf?
Yeah, the absolute fundamental one for host reachability is EVPN route type 2, the MSCIP advertisement route.
Type 2. Okay.
That's how a VTAPE, a virtual tunnel endpoint on one leaf, learns precisely where a host is attached on some remote leaf switch. It allows that direct VXLAN tunnel to be built for traffic.
Got it. So Type 2 is MS and IPs for hosts inside the fabric. Just quickly, why focus only on Type 2? Are there others we should briefly mention?
Good point. We focus on Type 2 because it's core to basic connectivity and mobility within the fabric. But yeah, there are others. Route Type 3 is important for handling B1 traffic broadcast, unknown unicast, multicast, setting up the right distribution trees.
Okay.
And then there's Route Type 5, which is more about advertising IP prefixes out of the fabric, like talking to your traditional network or the internet. But for that essential, where is this host? It's Type 2 doing the heavy lifting.
Excellent clarification. Okay, scalable physical network, check. Dynamic virtual overlay using BGP and EVPN Type 2, check. Now, the management headache. Hundreds of switches, tons of BGP and EVPN config lines. This is where automation becomes not just nice, but necessary, right? Enter Juniper Apstra.
Exactly. The complexity is the driver.
Apstra talks about defining intent.
Yeah.
You say what you want, not necessarily how to configure each box command by command, but something has to bridge that gap, yeah. How does my high-level intent become actual Junos CLI or whatever the switch speaks?
Right. And that translation piece is maybe the single most critical component in this intent-based networking model, at least operationally. It's done by the Apstra device agent.
An agent. So software running on the switches and routers themselves.
Precisely. Directly on the network devices.
Okay, that feels like a big step, giving an agent that much control. What's the advantage compared to just, scripting SSH pushes? What's this agent actually doing?
It's about moving from just pushing config to ensuring state. The agent takes the configuration that Apstra generates, they call it the rendered configuration, which comes from your overall intent,
Okay.
and translates that into the specific device commands, like Junos, EOS, whatever. But crucially, it also continuously monitors the actual operational state to the device and reports that back to the Apstra controller.
So it's a closed loop. It checks if reality matches the plan.
Exactly. It ensures idempotency, making sure the device state is what the intent says it should be. And if there's drift, the agent helps Apstra detect it and potentially correct it. It's fundamental to the whole IBN promise.
That makes sense. The agent is the eyes and hands on the ground, reporting back to the brain. Okay, let's talk design in Apstra. When an engineer starts building this fabric in the Apstra UI, what's the first kind of reusable piece they work with, the basic building block?
You start with something called rack types.
Rack types. Okay, like a template for a rack.
Pretty much, yeah. Think of it as your standard design for a physical rack. You define the logical bits inside, like, okay, this rack has 2 leaf switches, maybe some servers, maybe specific types of servers like compute or storage. And critically, you define their roles and how they're supposed to be cabled within that rack. Like server port 1 connects to leaf 1 port 10, server port 2 to leaf 2 port 10, that kind of detail.
So you define it once, and if you have, say, 50 identical racks,
You just reuse that rack type blueprint 50 times.
that must cut down errors massively.
Hugely. Standardizes cabling, roles, everything. Minimizes human error right at the physical and basic config level. So, okay, you've defined your physical rack structures with rack types. Now you need the virtual services on top.
Right, the actual tenant connectivity. If I need to set up layer 2 domains, layer 3 routing, VRFs, all that stuff for a specific tenant or application across the whole fabric, how is that handled in Apstra?
That's done using connectivity templates. You'll also hear them called virtual networks inside Apstra sometimes.
Connectivity templates or virtual networks? Got it.
These are the things that bundle up all the necessary L2 and L3 details. So you define your VLANs, your virtual routing instances, or VRFs, any specific routing policies, maybe BGP peering details for that tenant, all encapsulated in one template.
So you define tenant A network once.
And then you apply that connectivity template across all the relevant switches or interfaces in your fabric blueprint where tenant A needs service. Define once, deploy consistently everywhere. That's the goal for multi-tenancy.
Design once, reuse often. I like it. Okay, design covered. Now, operations. Day-to-day life cycle. Let's say a new leaf switch arrives. We rack it, cable it according to the rack type plan, and we get the Apstra agent installed and talking back to the controller. But we haven't actually pushed the real config yet, the one that makes it part of the working network. What status should we see for that switch in Apstra?
That's a specific and important state.
Yeah.
Out of service ready, or OOS ready.
OOS ready.
Yeah. It means Apstra sees the switch, the agent is running okay, it's physically connected as expected, basically saying, I'm here, I'm healthy, and I'm ready for my configuration. But it's not carrying any production traffic yet. It's like the final staging step before you commit it to the fabric.
The green light before hitting deploy. Makes sense. And just before Apstra does push that config to the OS-ready switch, what do we call that complete configuration file? The one generated from the whole blueprint, all the rack types, all the connectivity templates, everything combined.
That complete unified configuration derived directly from your intent is the rendered configuration.
Rendered configuration.
That's the single source of truth for the entire fabric's intended state at that specific point in time. That's what the agent pulls down and applies.
Okay. So design, deploy now, ongoing validation. How does Apstra make sure the network is actually doing what the intended? How does it continuously check that the operational reality matches the design, that things haven't drifted or broken silently?
That's the job of the intent-based analytics probes. or IBA probes.
IBA probes. Okay, the analytics part.
Right, these aren't just basic pings or SNMP checks. An IBA probe is designed to collect much richer data telemetry and analyze it specifically against the intent you define.
Can you give an example?
Sure. You can have an IBA probe that doesn't just check if BGP sessions are up. It could check if each BGP session has the expected number of routes based on your design, or verify that end-to-end latency between 2 points stays below a certain threshold, or confirm security policies are correctly enforced. It's about automatically detecting deviations from your specific intent.
So it's constantly watching, validating against the blueprint's goals. That sounds incredibly useful for catching problems early.
It is. It's proactive validation.
Things still go wrong sometimes, right? Maybe a change looks fine, gets deployed, but causes some weird, subtle issue later. What if we need to roll back? Is there a safety net? Like, can we see what changed and easily revert the whole fabric configuration back to how it was yesterday before the problem started?
Absolutely. That safety net feature is called Time Voyager.
Time Voyager, catchy name.
Yeah, and it's incredibly powerful. Think of it like Git or version control, but for your entire network fabric blueprint.
Ah, okay.
Every single change, every commit you make to the blueprint is recorded. You can visually inspect the history, see exactly what changed between different points in time, compare configurations.
That's a crucial part.
And you can select any previous commit point and roll the entire fabric blueprint back to that known good state with essentially a click, undoing potentially complex fabric-wide changes instantly. It's probably one of the biggest operational lifesavers Apstra offers.
Wow, okay. That capability alone seems worth the price of admission for managing complex fabrics. That really changes the game for change management.
It really does reduce risks significantly.
Okay, so here's a final thought for you to chew on, something to consider. If Apstra manages the intent and it uses these sophisticated IBA probes to constantly validate the operational state against that intent, does this closed-loop model mean we don't need traditional manual packet-level troubleshooting skills anymore? Or perhaps does it just shift where the deep human expertise is needed most, maybe less on CLI minutia, and more on understanding the automation system, the APIs, and how to craft the right intent and validation probes in the first place?
It's a good question to ponder.
We'll leave you with that thought. Until next time on The Deep Dive, keep digging.